You know, all around us, in signals we can't even see, there are these hidden stories just waiting to be told. The rhythm of a heartbeat, right? The tremor of an earthquake, the complex hum of a machine, they are all packed with information. But to actually decode them, well, you need the right tool. And that is exactly what we're going to dive into today.
So this is it. This is the big challenge for pretty much any scientist or engineer out there. How do you look at a complex, messy, real-world signal and pull out the one crucial pattern that really matters? How do you find the signal inside all that noise? For decades, analysts had a couple of ways of looking at these things, but both came with a really critical blind spot.
So on one side, you've got time domain analysis. This is great. It tells you exactly when something happens. On the other side, you have frequency domain analysis, which tells you what frequencies, think of them like musical notes, make up the signal. But here's the catch. For signals that change over time, which is basically all of them in the real world, you absolutely have to know both what and when, at the same time. Knowing one without the other is like having a list of all the notes in a song but with no rhythm or timing. You can't hear the music.
To solve this puzzle, we needed a completely new kind of tool, something that lets us see both time and frequency in one single beautiful picture. And this is where we bring in what you can basically think of as a mathematical microscope. The wavelet transform, or WT for short, is a total game changer. It doesn't just break a signal down into its component frequencies, it shows you how those frequencies are evolving and changing over time. It was built from the ground up to get around the problems of all those older methods.
See, the techniques that came before, like the short-time Fourier transform, were kind of like using a microscope with a fixed lens. You were just stuck with one level of resolution for everything, and that compromise meant you could never get a perfectly clear picture. Your view was always just a little bit blurry.
And this is where the wavelet transform just blows the old ways out of the water. It uses an adaptive grid. So for those super fast, high-frequency events, it gives you this incredibly sharp, precise view in time. But for the slow-moving, low-frequency trends, it gives you a broader, more accurate view of the frequency. It's called multi-resolution analysis, and it gives you the best of both worlds.
Okay, so we've got our super powerful microscope. Awesome. But every microscope needs a lens, right? Well, in the world of wavelets, these lenses are called mother wavelets, and this is where a whole new problem pops up. There are literally hundreds of them to choose from. Daube, Schies, Morley, the Mexican hat, and picking the right one for your specific signal, that's a huge challenge.
But what if you didn't have to choose from this massive library of fixed lenses? What if you had one, single, perfectly adjustable super lens that you could tune for any signal you could imagine? Well, that is the elegant solution offered by the Generalized Morse Wavelets.
Generalized Morse Wavelets, or GMWs, they're not just another wavelet, they're an entire family, all unified into one elegant equation. So instead of swapping out a whole new wavelet, you just tune two simple parameters. This makes them, as the research shows, the perfect starting point for almost any kind of analysis.
So what are these magic dials? Well, first, there's gamma. This one controls the wavelet symmetry. Second is beta, and that adjusts its duration, basically how long it looks at the signal. So let's say you're trying to find a really short, sharp spike. You'd want a shorter duration. If you're analyzing a long rolling wave, you'd want a longer one. Just by tweaking these two knobs, you can craft the perfect lens for whatever you're investigating.
And the range of things being investigated with this tool, it's just mind-blowing. It is being used in nearly every field of science you can think of.
I mean, think about it. In medicine, GMWS are being used to analyze brain waves from EEGs to automatically spot seizures. They're analyzing the tiny changes in a person's walk to help diagnose Parkinson's disease, and even decoding patterns in body temperature to track fevers in COVID patients.
Over in engineering, they're helping us understand the absolute chaos of turbulent fluids. They're diagnosing microscopic faults in the gigantic gearboxes of wind turbines, and they're monitoring the vibrations in a bridge to make sure it's structurally sound. This is all about making our world safer and more efficient. And the applications go from deep underground all the way to the air around us. Geoscientists are using GMWs on seismic data to find ancient riverbeds buried miles beneath our feet, while in communications, the exact same tool is analyzing Wi-Fi signals for indoor positioning or interpreting radar to recognize human activity.
So we have this unbelievably powerful, versatile, and finely tunable tool that's being used everywhere. But this is where the review paper we're looking at takes a really surprising turn, and it reveals something fascinating about how science is actually practiced.
The authors point out a paradox. They state that the parameters, those two dials, beta and gamma, are yet to be chosen through a rigorous methodology and argumentation. So, in other words, even with this amazingly adjustable tool, researchers often aren't explaining why they picked the settings they did.
Which leads to a fantastic question. If you give the world's scientists an instrument with two incredibly precise dials for fine-tuning their work, where do they actually set them? The answer is, well, that's pretty surprising. That first dial, gamma, the paper finds there's an almost universal consensus. Everybody sets it to 3. And there's a really, really good reason for this. A gamma of 3 creates the most symmetrical and efficient wavelet possible. It actually achieves what's known as the Heisenberg limit, which is the absolute theoretical maximum precision you can get. It is the mathematical sweet spot.
Okay, so what about the second dial? Well, it turns out the most common setting for a related property, the time bandwidth product, is 60. And the reason for this one, it isn't some kind of mathematical perfection. It's because this value, along with gamma equals 3, just happens to be the default setting in a lot of popular scientific software, like MATLAB.
And just look at this. This table just brilliantly illustrates what the paper found. Analyzing brainwaves to find seizures, the defaults. Diagnosing Parkinson's from how someone walks, the defaults. Assessing heart rate, analyzing turbulent fluids, finding faults in mechanical systems. Time and time again across wildly different fields, researchers are using the exact same out-of-the-box settings.
So here it is, the paper's core conclusion. We have this powerful, highly adaptable instrument that was designed for customized analysis, but in practice, a huge number of studies are simply using the factory default settings, and they often don't provide a rigorous argument that those settings are truly the best ones for their own specific, unique problem.
Now, this isn't a criticism, not at all. It's a fascinating observation about the path of least resistance in scientific research, and it leaves us with a really provocative final question. With a tool this powerful, what subtle patterns, what hidden clues, and what potential discoveries are we leaving on the table, just waiting for the next person who decides to turn the dials?